let us look at a systematic way, right? So let us look at a systematic way for determining the non-distinct power combinations using the ideas we saw in the previous slides. So take a random number, right? So take 2 power 18, and in the bottom up way, let us find out while computing 2 to the power 18, what are the other powers that get computed while finding 2 to the power 18, right? So let's just observe the power, right? 18. 18 can be written as 9 into 2, right? So I think I'm just throwing this out because you will get that idea. Now let's get a bit systematic. So let's go and ask what are the factor pairs of 18. So what is a factor, right? So what is a factor pair? A pair of numbers that when you multiply gives you the target is a factor pair, right? So 9 comma 2 is a factor pair of 18. So if you start from 1 and write out all the factor pairs of 18, so the factor pairs of 18 are 1 and 18. 1 into 18 is 18. 2 into 9, right? Again 18, and 3 into 6, right? And you don't have to go after that because you just have to go till the square root of 18, right? Because after the square root, you will get everything in the reverse order, like 18, 1, 9, 2, 6, 3. But you would have already found out, right? Because if the square root itself is that number, then anything above the square root, you can't find a factor pair with two bigger numbers greater than the square root. It's a logic, right? So you just have to go till the square root of 18 to list out all the possible factor pairs of 18, and this is the factor pairs that you get for 18. So it's 1 18, 2 9, and 3 6, right? So 4 into 4 is 16, and the square root of 18 is somewhere around that, right? It's like 4 point something it will be. So there is no need to go after that. Now let's get to the key idea. So 2 to the power 18, now you use each factor pair and write that 18 in terms of the power law formula we knew in our high school math. So 2 to the power 18 using the first factor pair 1 comma 18 can be written like this. 2 to the power 1 power 18 and 2 to the power 18 to the power 1, right? So you will see the beauty, right? So just hang on with me. So write the same thing with the second factor pair. So 2 to the power 18 can be with the second factor pair, you write it as 2 to the power 2 power 9. Now happens the magic, right? So what is 2 to the power 2? It is 4. So 4 to the power 9. So that is a non-distinct power, right? So 2 to the power 18 is the same value as 4 to the power 9. And then again you swap it, right? So 2 into 9 is 18 and 9 into 2 is also 18. So now instead of writing 2 to the power 2 power 9, you write now like this: 2 to the power 9 power 2. So 2 to the power 9 is 512 power 2, right? And it's a 512 to the power 2 is actually the same value. So it's a non-distinct power of 2 power 18. And go to the next factor pair, 3 comma 6. So 2 power 18 can be written as 2 power 3 power 6, which is nothing but 8 power 6, and you swap it 6 comma 3. So 2 power 6 power 3, again 6 3s are 18, but 2 power 6 is 64 now. So it is 64 power 3. So now what you have got by finding out the factor pairs of the power and expressing that power as a factor multiple and using the power law, you are getting the different non-distinct combinations that yields the same value as 2 power 18. So while computing 2 power 18, we end up computing the values for 4 power 9, 512 power 2, 8 power 6, and 64 power 3, right? That's what we end up getting. So now you know why I didn't give much attention to this one, right? Because 2 to the power 1 power 18 is the same, and 2 to the power 18 also is the same, right? So that's why 1 comma 18 I didn't take much in my example, but anyways it will be the non-distinct value. 2 power 18 will be the non-distinct value, but everything else 4 power 9, 512 power 2, 64 power 3, and 8 power 6 will be non-distinct. This will be distinct. 2 power 18 will be distinct. And if you look at the cell values, so 2 power 18 will have the value 1, right? As per our logic, it is the first distinct value. But 2 power 18, because it is giving the values of the rest of the powers, 4 comma 9, 8 comma 6 and 64 comma 3. These cells correspond to 4 power 9, 8 power 6 and 64 power 3 will have the value minus 1. So if you see, I have excluded 512 power 2. Why? Because our problem range is between 2 to 100 only, right? So that is the reason. Actually, you don't have to worry about if. So all that you need to remember is, if the base is going to yield a value which is greater than 100, you can ignore that combination. So the highest that 2 can go is like 2 power 6, right? So 2 power 6 is 64. So 2 power 7 is like 128, right? So anything above 6 you can just exclude, because the base is going to fall beyond the ask of the product's problems range. And that's why if you see, I have excluded 512 power 2, even though it's a non-distinct value that is computed while finding out 2 power 18. So whatever bases and powers that lie within the problem's range, A to the B, in the range of 2 to 100 is what I have included here. So just by using a simple technique, what did we do? We did a power swapping. So we did a listing out of factors in a systematic way, right? So we listed, so what is the power? Take the power, find the factor pairs of that power, then express that target power as its factors. Now, if the base to the factor is within 100, then count it as a different one, right? So 2 to the power 4, 2 to the power 2 is 4 to the power 9. So then you get it. So now once you start expressing it in this way, you are going to find out in a bottom up computation. So while computing a smaller power 2 to the power 18, what are the other bigger powers you end up computing, which is 4 power 9, 8 power 6 and 64 power 3, and make them as minus 1, because they are all non-distinct power combinations, and make 2 power 18 as 1 because it's a distinct power combination. So this is a systematic way to go around and finding out the non-distinct power combinations in a bottom-up way, right?